today's topic is amplitude modulation. It falls into your LO number 1 and 2, and a little bit in LO number 3. This is from chapter 3 of Frenzel book, which is Amplitude Modulation Fundamentals. We discuss the concept of AM, then modulation index and percentage of modulation, sideband and frequency domain, AM power, and sideband modulation. For today, we may cover number 1, 2, and maybe part of number 3, or maybe we can stop at before part 3. Okay, so what is generally AM modulation? In the modulation process, the voice, video, or digital signal modifies another signal called the carrier. In amplitude modulation, the information signal varies the amplitude of the carrier signal wave or carrier sine wave. So we have a message signal and we have a carrier signal. So the carrier signal will carry the message, and the shape of that carrier sine wave will be changed based on the message signal. The instantaneous value of the carrier amplitude changes in accordance with the amplitude and frequency variations of the message signal. An imaginary line called the envelope connects the peak of the carrier waveform. So I will show you after this. So let's see, this is our message signal. Usually, message signal is not sinusoidal, but of course there is some condition. We call it tone communication. We may send a sine wave as our message. When we refer to message, usually, or modulating signal, usually they are in lower frequency, like voice, maybe like your data from your computer. So in this example we are showing in my lecture, most of the modulating signal is also a sine wave. So for better understanding and better presentation. And carrier is also a sine or cosine wave, but higher frequency, much higher frequency. Then this is, for example, at the beginning we have a carrier. If you follow my mouse, this was the level of my carrier initially. So then it has been modulated with the message signal, or message signal has been modulated with the carrier. Then now you can see my carrier peaks has been changed. So you can see is getting a shape of sine wave, which was this sine wave. And if you connect or join all the peaks, or maybe all the minimum parts, the shape becomes sine wave shape, which is similar to our modulating signal. This is what we say the carrier takes the shape of the message signal or modulating signal. And if you join these peaks, as you can see, not very clear line shown here. We also call this as an envelope. So if you, is like plotting, if you take all these peaks as a point and connect them together, then it becomes something like sine wave. And that sine wave should be the same as your message signal. In fact, it will be similar to your message signal if this is a amplitude modulation and if it is correctly modulated. So this red color higher frequency signal is the carrier. This is also showing a amplitude modulation, and it shows like this. So means these lines representing higher frequency, the orange color signal showing your message. So okay, how we can mathematically represent our signal, our carrier, and our modulated signal using trigonometric functions. We can express the sine wave carrier with the simple expression here. So we have VC. Okay, just take care. In this book, the VC equal to another VC sine 2 pi FCT. These two, both of them called VC, only the writing formats are different. In many books, this amplitude are AC, so then your voltage is equal to the AC means amplitude of sine, but here it took as a voltage. So voltage means the peak voltage. Here I show you where is the peak voltage, VC. So mathematically, if we have a sine wave, we can just write in this form. The first coefficient behind the sine representing the peak. Since this is started from 0 going to peak is a sine wave. But if it's a start from 0 and going to start negative, it will be phase shifted of sine. But if it's cosine, it will be started from the peak, means 90 degree later. So the carrier, by the way, can be sine or can be cosine, or can be phase shifted version of any of them. Here we just shown a sine wave with 0 angle. So then this is a sine wave. The angular velocity is 2 pi FC. FC means frequency of the carrier. Later we may have our message. It has also a frequency. To easily distinguish between them, the carrier we put FC, message we put FM. So T represent the time variation of the signal. VC also should be by right time variable. We should show VCT because it is also a time variable signal. But in the books, we may not show them, or we just consider as instantaneous value. So this is equation or mathematical representation of this waveform. So this is our equation, VC equal to VC sine 2 pi FC or omega C times T. The VC represent the first VC, represent the instantaneous value of the carrier sine wave at some specific time in the cycle. VC, which is the peak, represent the peak value of the carrier. and Fc represent the frequency of the sine wave or the carrier. T represent the time. We can also show this for our message signal. But if the message signal is a sine wave, here in our case, we are showing our message signal as a sine wave, then we say Vm equal to maximum, the peak of the sine wave, which here is Vm sine 2 pi fmt. But in many cases, your message could be a voice, and you don't know what is your voice function. So in that case, you just need to show, for example, Vm or Xm as your voice message. But you don't have that frequency, and you may not know what is the peak as well, because that is also keep changing. Similarly, the capital Vm is the peak of your sine wave message. Fm is the frequency of your message. A modulator is a circuit used to produce amplitude modulation. Amplitude modulators compute the product of the carrier and modulating signal. So this product here doesn't mean multiplication. So it just means produce. So inside of this modulator, there are few functions happening. It could be a summation, there could be summation and a multiplication. So the input is of a message. The message can be anything. Can be a video, can be a voice, can be a data. Here we assume is a sine wave, which we show here our sine wave equation. Carrier can be a sine or cosine wave with a little bit, not a little bit, is much higher frequency than your message. And then inside there will be some process happen and the modulation will be happen. Usually there is like a adder and a multiplier. So then at the end we have something like what we write in this example. And remember, this is not the unique design. You may have a little bit different design as in the modulator, but the output is relatively similar parts. So what are the parts? There is a carrier signal plus the message signal times the carrier. But the amplitude of them or the peak of them could be different. But this is one type, which we will see how it comes to this calculation. So the instantaneous value of the top voltage envelope V1 can be computed by this equation. So means VC plus VM. Okay, I show you the next slide first. You can understand better. Now we know our message signal is just a sine wave with the peak of Vm. The whole equation represented by this, let's say, a small Vm. Then we have a carrier. After we do modulation, what is the peak of this signal? If we take the peak of this signal, as I show here, we write it as V1 equal to capital VC, which is the peak of the carrier, plus the whole equation of the message signal. The reason why we write the whole equation of the message signal, because the variation of the envelope or the variation of the modulated signal is same as our equation which we define for the message signal. So that's why we write this small letter VM. So we didn't put just the peak because the variation of this can't be really explained with only the max value. So if we define this, then we can substitute VM inside of this, and then we can have V1, a longer equation, which I didn't show here, I show here. So as we said, V1 is VC plus a small letter VM equal to VC, capital VC is the same. VM, we substitute VM sine 2 pi FMT here. And then we can say this is now our modulated signal, which is V1. As V1 is representing like the peak, and it is a sine 2 pi FCT. So this is higher frequency, is carrier frequency, and is a sine wave. Only the peaks are keep changing. How the peaks are changing is based on V1. So that's why we put V1 as a peak representation of the peak variation, sine 2 pi FCT representing how our carrier sine wave is, the frequency is. Now we have our AM signal or equation is V1 sine 2 pi FCT. Now if I substitute V1 here, which is VC plus a small VM, we get this, which I show in previous slide. So if our VAM is V1 sine 2 pi FCT, I can substitute V1 from our first equation here inside. Then what I have is the whole equation of V1 should be multiplied by sine 2 pi FCT. So which is here, VC plus VM sine 2 pi FMT, which is this, multiplied by sine 2 pi FCT. So if you multiply this, you have VC times this sine 2 pi FCT, which is this, become this. Then your VM sine 2 pi FMT will be also multiplied by this carrier. So you have two signs here. One is representing your message, another representing your carrier. So means you have two parts in your modulated signal. One is only carrier, another one is carrier times message signal. So in fact, the information of the message is in the second part of the equation. The first part is just the carrier and maybe just carry some power, but the other part is the actual message there is. Okay. Same thing here, what we discussed is here shown by illustration, shown also the signal. Okay, so then this is one example of amplitude modulator. So means I am showing you how we can make an amplitude modulator. It's just a block diagram, how to get some waveform or mathematically something like a amplitude modulation. So let's say MT is our message signal. So here I change the letter of the message. I put as a MT is a time variable, maybe is a voice, for example. This come first, we combine this with a DC bias. The reason why we want to add a DC bias, we want to bias it to bring it the amplitude up. So later I will show you why we do this. After we bias this with a DC value, here my DC is, I just take 1 volt, but could be, of course, a different value. Then the output of this is message signal plus 1 volt, let's say, biased DC. It becomes 1 plus MT. Means whatever your message signal was, it has just shifted up the level in terms of y-axis. The amplitude goes up. The whole thing, I mean, become up. So the concept is we separate them from the x-axis as much as possible to not have any crossing the sign, I mean the x-axis. Similar to what you see here, this message signal is even the minimum part of the message signal is still above the x-axis to not cross the x-axis. Because if that happens, if it cross, there will be something, we call it distortion, and we cannot do amplitude modulation because the shape of your envelope won't be the same as your message. So that's why we don't want to do that. We try to make sure our message is all above the x-axis. So not crossing the x-axis. So that's why we bias it with the DC value. So now I have 1 plus, this 1 could be a DC value, any value, plus the message signal. It comes to a multiplier. So this is multiply the 1 plus MT with a carrier. Here we take the carrier as AC. AC is just the amplitude of the carrier or sine wave. Sine omega ct, omega c represent 2 pi f ct. 2 pi fc. So AC sine omega ct multiplied by 1 plus mt. Then the output, I put xct, become equal to this, which is AC sine omega ct times 1 plus mt. Now, if you multiply this, here I am continuing. If you multiply this carrier to this 1 plus mt, you have 2 terms. One is AC sine omega ct plus your message signal times the carrier, mt times AC sine omega ct. So this is for general form, very similar it is to our previous equation. We have amplitude of the carrier times a sine wave, which has fc, carrier frequency, plus a message signal. Here the message signal was sine wave, but in our new example I shown is just empty, and there is a carrier frequency, a carrier signal as well, which is sine 2 pi fct. Here the carrier amplitude is not available, but here our carrier amplitude is available. So that is the only difference between the two. But this is one example of also amplitude modulation. Now, if I take my message signal, let's say to say is a sine wave, let's say sine wave has an amplitude of AM, sine wave with frequency of omega m or 2 pi fmt. And if I substitute instead of mt, I put am sine omega mt, I have this signal, which is carrier plus message signal times the carrier. So this is one example how we can make a modulator. In fact, modulator, I mean amplitude modulator is a simple electronic circuit. So you have your message. If it is voice, could be you receive the voice in electrical form, or maybe you directly put the microphone and talk to the microphone. The microphone convert your message, I mean your voice, to electrical signal. Then you put just a DC and adder to combine them. Then put a multiplier, and you need to put you need a clock frequency generator or sine wave generator, which you can adjust your frequency, and then multiply these two, and then you have your output, which it can transmit your signal. Okay, so there are something which we need to follow, or we need to understand to have a correct amplitude modulation. One of them was, as I said, we should make sure our message signal is above the x-axis, is not crossing there. This, in other words, meaning that the message signal, the peak of your message signal should be always smaller than the peak of the carrier signal. So in AM, it is particularly important that the peak value of the modulating signal be less than the peak value of the carrier. So means the carrier peak should be larger than the message. So based on that, we define modulation index, representing by M, is a value that describes the relationship between the amplitude of the modulating signal and the amplitude of the carrier signal. So M is Vm over Vc. This index is also known as the modulating factor or coefficient, or the degree of modulation, and it should be always less than 1. So less than 1 means Vm, message signal peak, is always smaller than Vc. If both of them are the same, it becomes 1. Still 1 is acceptable, but should not be larger than 1. So Some books may show this m as mu, but here in this book it shows as m. Multiplying the modulation index by 100 gives the index in the percentage form, and then we can talk about percentage, means the ratio between the peak of the modulating signal to the peak of the carrier signal become in the percentage form. If both of them are the same, become, let's say, 100%. For example, if the carrier voltage is 9 volt and the modulating signal voltage is 7.5 volts, the modulating factor or index is Vm over Vc, become 7.5 divided by 9 is 0.83, and the percentage of modulation is 83.33%. So this is, we say our modulation index is 83%. So here, distortion occurs when the amplitude of the modulating signal is greater than amplitude of the carrier. So if m is larger than 1, let's say this our signal was sine wave, just as example, but now you can see your envelope is no more sine wave. You see here, this goes to the peak of sine, then goes to the minimum part of the sine, but our amplitude modulation, the envelope supposed to be the same shape as the message signal. Later I show you the demodulator. The demodulator only understands this envelope, doesn't understand this shape. So that's why here distortion happens. As I said earlier, we don't want our message cross the x-axis. We should bias it to go above to the x-axis. So whatever our peak to peak of the message signal is, they should be above the x-axis, or we should put a DC value to push them up. So when they multiply by the carrier, we have an envelope exactly the same shape as the message signal. So this is one distortion we call also over-modulated wave. So now we did over-modulation, and this signal cannot be detected at the receiver. We can, of course, detect, but some part of your message will be lost or become like something you don't understand. So let's say this was a speaking, or if it is, of course, let's say it was sine wave, it was, then you won't get a nice sine wave. What you get is, here is looks like sine, then you have a small peak here, then you have sine, like sine, then is not really sine wave. So the over-modulation and distortion happen based on what we are discussing. The modulation index should be a number between 0 and 1 to avoid over-modulation or distortion happen. If the amplitude of the modulating voltage is higher than the carrier voltage, M will be greater than 1, causing distortion or over-modulation. If the distortion is great enough, the demodulated signal becomes unclear or impossible to understand. Let's say if it is a voice, what you receive is something you can't understand what the message is. It becomes noisy. Over modulation again, continue. So this distortion of voice transmission produces a strange distorted sound or unnatural sound in the speaker. So this is if distortion happen or overmodulation happen. Distortion of video signals produces a scrambled and inaccurate picture on a TV screen. And of course, depend on how serious is the distortion. The ideal condition for AM is when the peak value of your message is equal to the peak of the carrier, or M is equal to 1, or we call it 100% modulation. So that is the most ideal case because we have maximum power in the AM modulation. So this is another example of envelope which have distortion. You can see here is clipping, means your sine wave is just cut. So the waveform is flattened at the 0 line. The received signal will produce an output waveform in the shape of the envelope, which you see is like this shape. Here is like a sine wave, then suddenly become cut. Like a sine wave, suddenly cut. Which in this case is a sine wave whose negative peaks have been clipped up. So means when you detect this signal at the receiver, you will have a sine wave. The top peak maximum is just okay, but the minimum part all are cut or clipped. So this is another example similar to this is also another distorted example. Percentage of modulation. So the modulation index is commonly computed from measurements taken on the composite modulated waveform. So means when we have modulated signal, then we can get modulation index. So for example, if we have oscilloscope and our modulated signal is shown in the oscilloscope, we can calculate the parameters of the message. I mean, the parameters of the index, for example, VM, VC, and also the modulation index. We can calculate from the modulated signal shown in the oscilloscope, for example. The amount or depth of AM is then expressed as the percentage of modulation, which is 100 times M, rather than a fraction. So we show by percentage, as we said. So let's see how we can find or calculate VM, VC, and M from the oscilloscope signal. Here, let's say, showing our oscilloscope, and then what you have is a modulated signal. You have this waveform maybe. Of course, your oscilloscope only show this high frequency, doesn't show the orange color envelope. or the red color if you see red. So it just show the high frequency elements. So, but you can find the values here. The peak of your modulated signal to the 0 or x-axis, this is, we call it Vmax. Then from the minimum part of your positive part of the signal to x-axis, we call it V min. So we have Vmax and V min. So we also have V min peak to peak. We have Vmax peak to peak as well. So Vmax peak to peak is 2 times of Vmax. V min peak to peak also is 2 times of V min. If you, just as example for your understanding, if you are running a modulation with index of 100%, this mean will be exactly touching the x-axis, and V min peak to peak become just 0. Just as example. Okay, how we can write Vm? So the Vm means the peak of your message is Vmax minus Vmin. So Vmax minus Vmin means from this peak to this negative part, to this min, from peak to, or from max to this min point. This represents your Vm. So we see the carrier amplitude or carrier voltage is Vmax plus V min divided by 2 as well. So Vm equal to Vmax minus V min become your message signal amplitude. Your carrier voltage, if you want to know how much was your carrier voltage, is Vmax plus Vmin, then divided by 2 is your carrier voltage, and the modulation index is Vm over Vc, which is Vm minus V min divided Vmax plus V min. Since both of them as divided by 2 will be cancelled, so what you have is Vmax minus Vm over Vmax plus Vm. So that is your, how you can calculate the 3 parameters from modulated signal. So here I want to show you an example of amplitude demodulator using envelope detection. So envelope detection is just a simple electronic circuit. There is a diode which will first pass only one section of your message, means the either positive or negative can be clipped or removed. So here we cut the negative parts, then the voltage will be here on the R1, then it will comes to a capacitor. So what happened, every cycle is changing when the voltage is going, or the carrier going towards the peak, the capacitors will be charged, and Then while it's going towards the negative part, they discharge, and that voltage will be released to the R2, which is our output voltage. So this is going to our V in, I mean the whole message. Then this voltage going to our capacitor is this voltage, which is like a charging and discharging, and our output will be just the peak of this. We do a little bit filter this to remove all this vibration or variation. What we have in the output is a smooth signal, which is similar shape as the envelope. So that is how a demodulator convert your incoming signal to your original signal. Now you imagine if there was a distortion here, then this couldn't detect it or become wrongly. This maybe become positive part. So this is a simple envelope detector or AM demodulator. Of course, not all AM demodulators are similar, but this is just one example for your understanding. Okay, sideband or side frequencies or sidebands are generated as part of the modulation process and occur in the frequency spectrum directly above and below the carrier frequency. Let's see what these sidebands are. So here I want to show you the sidebands frequency calculation. Single frequency sine wave modulating signal generates two sidebands. This is very important. Remember, what I am discussing refer to a message signal, which is a sine wave. And a sine wave has only one fundamental frequency. The meaning of single frequency sine wave means have only one fundamental frequency, and we use that as a modulating signal, as a message. If you use such a signal as your message, when you modulate with a carrier, you have two sidebands only. But if you have like a square wave signal, you don't have one fundamental frequency. As I said previously, in square or rectangular waves, you have one fundamental frequency plus harmonics. Each harmonics also produce sidebands, which that is not my discussion now. I am talking about a single sine wave which only produce two sidebands. We want to show you how that is, then you can understand the rest. But complex waves, voice or videos, if they are as a modulating signal, generates a range of sidebands. The upper sideband usually we show F, USB, and the lower sideband we show F, LSB, means this is frequency of lower sideband and this is frequency of upper sideband. How we calculate is like this, very simple. Frequency of upper sideband is carrier frequency plus frequency of the message. When we say frequency of the message, means the maximum frequency of the message. And FC, of course, is a carrier frequency, I assume is sine wave form, and they have one frequency. Lower sideband is carrier frequency minus maximum frequency of the message, where FC is the carrier frequency and FM is modulating frequency. So, of course, if it is a single frequency sine wave, FM also is one frequency. There is no maximum. But if it's a voice, you need to look at the maximum frequency. Okay. So the existence of sidebands can be demonstrated mathematically, starting with the equation for an AM signal we described earlier. So let's say this is our AM modulated signal, which we mentioned earlier. If we use this simple trigonometric relation, which is sine A times sine B, here we have two sine, you remember? Sine with frequency of FM, sine with frequency of FC. So sine A means this, the argument, which is 2 pi FMT, let's say is A. And B is 2 pi FCT, we say B. This amplitude is just fine, can be multiplied to the whole equation. So if you have such a multiplication of two sines with two different frequencies, then you can write it equivalent to cosine A minus B, means frequency A minus frequency B, then the amplitude divided by 2 minus cosine frequency A plus frequency B divided by 2, means the amplitude divided by 2. So in our case, if we convert this based on this trigonometric relation, we have our modulated signal. The carrier part remains the same, plus Vm divided by 2 because of this division, times this sine become cosine 2 pi t times Fc minus Fm. So means F, or you may say cosine omega c minus omega m, minus Vm over 2 cosine 2 pi t Fc plus Fm. So here carrier frequency is minus message frequency, then the total frequency become a little bit lower, we call it lower sideband. Here we have carrier frequency plus the message frequency, the total frequency become a little bit higher, we call it upper sideband. So this is how we can represent our modulated signal in terms of lower and upper sidebands. Here I have one example. Assume that a 400 Hertz tone modulates 300 kilohertz carrier. Tone means just a sine wave. We call it tone sometimes. So means 400 Hertz modulating signals is modulated with a carrier of 300 kilohertz. So you can see the modulator is much higher frequency than the message signal. The upper and lower sidebands are, the upper sideband is frequency of the carrier plus the frequency of the message. 3000 plus 400 become 3400 or 300.4 kilohertz. Lower sideband is 3000 minus 400 become 299,600 or 299.6 kilohertz. This is how you can calculate your upper and lower sidebands if you have the frequencies. So this shows time domain signals for the message signal, the lower sideband, which has lower frequency, the carrier, upper sideband. So if you count these peaks, for example, the carrier has how many peaks during this time? You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is about 5.5 cycles, or we just refer to, let's say, peaks, 11 peaks. Lower sideband should has a little bit lower number of peaks. So you count it 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you check, the upper sideband should have a little bit more number of peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there is a little bit extra here. This 11 was a starting line, finish to the starting line. But this started a little bit later, and or if you compare the minimum peaks, there is extra. So that shows your upper sideband has a little bit higher frequency, lower sideband has a little bit lower frequency compared to the carrier. Combining all together is this, what you see as our modulated signal. That was in time domain. In frequency domain, you see these three maybe line or frequencies. The center part is carrier frequency. This is upper sideband, which is a little bit large, higher frequency than carrier. Lower sideband is a little bit in the lower part. So you have in the frequency domain. Okay, so let me stop at this slide.